All right, I'm going to talk about functions and their properties, and specifically in this quick video, we're going to talk about domain and range, and that's a big deal in the math that we're going to do going forward in this chapter. Okay, so let's talk about functions and their properties. The first thing we're going to talk about is what is a function. Well, what a function is a relation that has for every x exactly one y, or exactly one input for every output number. Um, but you might say, okay, well, what's a relation? Well, a relation is a set of ordered pairs that has a specific set of input values and then another that are output values. And a very common relation is one that you learned in Algebra 2, or if you learned it in pre-cal, which is a unit circle. So the unit circle is a famous relation. So I'm going to draw the unit circle here. Here we go. Unit circle is a circle centered at the origin that has a radius of 1. And its equation, this radius is 1, is x squared plus y squared equals 1. And this is not a function because if I were to plot a point at this x value, if I were to go up, I have a y value for that x value here, and I have another y value for that x value here. And I don't have just one value of y for this x, I have two. And there's a famous test called the vertical line test that if you were to do a vertical line with your pencil, or mentally even, from left to right, does my pencil or my line hit the curve more than once? And the answer is yes. I have two y values here. And so this is a relation. There's another kind of a relation that is an ellipse. And this one will be centered at 0, 0 again. And this would be x squared over a squared plus y squared over b squared equals 1 if I do it in graphing form. And that, of course, also fails the vertical line test. All right, well, what about a hyperbola? Hyperbola, if I graph it this way, fails the vertical line test. And that one is the only difference is I'm going to take this plus and make it a minus. So this would be x squared minus y squared equals 1 if I have a squared and b squared here. Okay, so those are some pretty amazing relations. In addition, you can have a relation that is a sideways parabola that opens to the right. And that one we could say is x equals y squared. And this clearly is also a relation because it fails the vertical line test. All right, let's talk about functions. This is a relation, and a function is a subset of the set of relations that has exactly one output number for each input. Okay, so there are some famous ones. We have y equals x. That is a function because it passes the vertical line test. We have y equals x squared, another good one. Y equals x cubed. Y equals the square root of x. And we could go on and on here. Well, what about our famous trig functions that we just got away from? Is y equals sine x a function? The answer is sure. Because even if it oscillates infinitely, if we were to do the vertical line test, it certainly passes it. And tangent and all of those functions that we did, or all those trig equations we graphed were all functions. All right, well, a function or a relation both have domains and ranges. Okay, so the domains are all the input values for which the rule applies, and the range is all the output values. Now, typically, we would say domain is the x values, and the range is the y values. And we would call this the independent variable. and the y values, the dependent variables. Now, we don't have to be stuck with x and y, because we could have functions of r, we could have functions of t, we can have functions with different variables, but a lot of times we'll use the x and the y. All right, so I have some pictures here, and we're going to determine whether the graphs are relations or functions, and then we're going to state their domains and ranges. All right, so we have to pretend that there are arrows here because I meant to have arrows here. And of course, this is a relation. I just suggested that this is a hyperbola, and it has a domain. That means all the possible values for x this function might have that we can use. So I can go move my pencil from left to right, and I can hit the function. Everywhere I hit the function for that value of x, I have a domain. So this is -2, by the way. So the domain here is going to be -infinity to -2 with a bracket. And then we start hitting values for x again at 2. So union with 2 to infinity. All right, now the range. That means I'm going to take my pencil and we're going to go, well, what y values does this relation have? Well, this relation has y values from -infinity all the way to positive infinity. So we'll go right -infinity to infinity and move on to the next one. This one here is a line with a negative slope. Is this a function? Does it pass a vertical line test? I would say yes. For every x, there's exactly one y. So this one's a function. Its domain is clearly all real numbers. And I like interval notation. Its range is, again, all real numbers. And this one is a function. All right. This one right here, is this a function or a relation? Now I want to make a mental note here. This is an open dot. This is open. And this one is closed. So this is a piecewise function. And let's see, do I hit x values? Because this is an arrow here and this is an arrow here. For all values of x? I do. So this one we say is a function. And its domain is all real numbers. And its range, this was a little bit trickier. I'm going to hit y values from -infinity until I hit this open dot here. And that's at 1, 2, 3, if you look at the graph. So this is going to be open, -infinity to 3, open, because I don't ever reach 3. Okay. Now, if this dot was closed, this would be a relation. But since this dot's open, and I have only one value, a one y value for this x at 0, then this would be a function. All right, this is a circle with a radius 2. And it's a relation because clearly it fails the vertical line test. So this is a relation. Its domain, even circles have domain, so I'm going to hit, this center is not part of it. I hit y values when I hit to negative, or x values when I hit to -2 to 2. So with brackets here, it's -2 to 2. And then I hit y values at -2 to 2. So the domain and the range are the same. Those are the possible x and y values. All right, so this curve right here is a rational function, and this is an asymptote here, so it's dashed. It's not part of a curve, and this goes to infinity, and this approaches 0. And this is a horizontal asymptote. So is this a function or a relation? If I were to do the vertical line test, I hope you can see that this one is also a function. Its domain is, well, I hit the function until x gets to, this is 2. So this is going to be -infinity to 2, open, union, 2 to infinity, because I hop over the vertical asymptote and then I have more function. All right, what about the range? Well, I'm going to hit, this is an arrow down here, I'm going to hit y values from -infinity until I get to 0, and I hop over 0 and then go from 0 to infinity. So the range is -infinity to 0, exclusive, union, 0 to infinity, and it is exclusive there, okay? All nothing new, I hope. Just a quick review. All right, so now, moving on, we're going to talk about some functions and whether we can determine their domain and range. Now this says graph the functions with your calculator and find the domain and range of each. But in pre-cal, I think we know that we can graph these by hand. This is the absolute value function shifted to the right by 5. So let's do that. 1, 2, 3, 4, 5. And then my absolute value function looks like this. The well-known v function here, absolute value. All right, so I want to find the domain. The domain here is going to be all real numbers. And the range goes from 0 with a bracket to infinity. Now, this says to find the domain and range, but let's talk about some interesting features here. This function, is it continuous? I would say it's continuous for all real numbers. And it has an absolute min of 0 at x equals 5. Does it have any increasing or decreasing intervals? Well, the function, if I put my finger on it, is decreasing until I get to 5. So this one is decreasing from negative infinity to 5. And it's increasing from 5 to infinity. If I were to put my finger on this function, it's going up from 5 to infinity. All right. And behavior limits. The limit as x goes to positive infinity. That means if I'm standing at positive infinity over here and I look up and down, my function is headed where? It's headed to infinity. So that limits infinity. The limit as x goes to negative infinity of f of x is equal to, as I go to negative infinity in the x direction, my y is going to positive infinity. All right. So those are some other properties of functions. All right, so let's move along to f of x equals the square root of x plus 2. Well, this is the square root function shifted to the left by 2. So here we go, we're going to shift it to the left by 2, and it looks like the square root function there. And this one has a domain it's inclusive of negative 2 to infinity, and it's got a range inclusive of 0 to infinity. This one is continuous. I'm going to put a bracket here, from 0 to infinity. And it has an absolute min of 0 at x equals negative 2. And this function is always increasing, isn't it? Always increasing. So we would say increasing from negative 2 to infinity. And it's never decreasing. So we would say not applicable. Right? We don't have any decreasing intervals. And it's end behavior limits. So limit as x goes to infinity of f of x in this case. That means as x gets closer and closer to infinity, the y is going to infinity, although it's getting there very slowly. The limit as x goes to negative infinity of f of x is equal to, now, so if I take x to negative infinity, does my function even exist over here? And the answer is no, so you would put d and e here. It does not exist at that location. Okay, so let's keep going. All right, x squared minus 2x minus 8. Well, that's a parabola that opens up. But in order to be able to determine the range, we have to know its vertex. So how do we find the vertex of a parabola? Well, I heard somebody in the crowd say it. Oh, Mrs. Muller, we got to find the vertex. How do we find the vertex? Well, to find the vertex, you got to complete the square. Ooh, I hear some moans. Okay, so to complete the square, let's see, we've got f of x equals x squared minus 2x minus 8. I'm going to rewrite that as y equals x squared minus 2x minus 8. Now this is how I teach completing the square. I say that you should take the constant and put it on the other side. So we're going to do that. We're going to say y plus 8 equals x squared minus 2x plus something. I got to complete the square here. But if I add something to this side of the equation, I have to add it to that side so they're still equal. So this is going to be plus something over here. All right, well, the plus something is I take half of this middle number. Well, what's the half of the number? Half of negative 2 is negative 1, and I square it. So it's negative 1 squared. So negative 1 quantity squared. I have to add it to both sides. So this is going to be 1, because negative 1 times negative 1 is 1. So this is going to be y plus 9 equals x squared minus 2x plus 1. And now we have a perfect square. This is y plus 9 equals x minus 1 quantity squared. I'm almost done, so we have y equals x minus 1 quantity squared minus 9. And my vertex, if you recall, vertex form for quadratics is y equals a times x minus h quantity squared plus k. And the vertex here is h comma k. So what's h here? H is 1 and k is negative 9. So my vertex in this case is 1, negative 9. So I'm going to take that information that we just did, completing the square, and I'm going to bring it over here. So it's 1, negative 9, 1, negative 9. Here's my vertex. And this opens up. Well, it opens up, and wouldn't it be nice to be able to find the zeros to this? Oops, can't spell. Finding zeros of quadratics. Well, how do we do that? Well, there's two ways. Well, three ways, actually. We completed the square, but I'm going to say y equals x squared minus 2x plus minus 8. Let's drop it a line so my g doesn't get hung up there. Y equals x squared minus 2x minus 8. Factoring, you're right. I heard somebody say factoring. So here we go. What are the factors of x squared? Well, they're x, and the factors of 8 that might add up to 4. Well, add up to 2. This is going to be 4 and 2. And the inner product here, 4x, and the outer product have to sum to negative 2x. So this will be negative 4x, and this is plus 2. And so if I set this equal to 0, my zeros are x equals negative 2 and 4. So I'm going to go to my sketch really quick. 1, 2, 3, 4, I have a 0. And 1, 2, negative 2, I have a 0. And then what's really cool in standard form is if I plug in x equals 0, I can see with a y-intercept here, which is negative 8. So that's going to be negative 8 right here. And then I'm going to draw my function, my beautiful parabola and its vertex. Okay, now we can do the domain. The domain we already know is negative infinity to infinity. The range here given to us by our vertex, when do we start hitting y values? We start hitting them at negative 9. So this is inclusive of negative 9 to infinity, the range. This is continuous from negative infinity to infinity. It's got an absolute min of negative 9 at x equals 1, because this is 1. And it's increasing from 1 to infinity. It's decreasing from negative infinity to 1. And its end behavior limits are the limit as x goes to infinity of f of x, and the limit as x goes to negative infinity of f of x. So we have to imagine ourselves at x equals positive infinity, and where is the y headed? It's headed to infinity, so this is equal to infinity. If I have the x going to negative infinity, where's the y approaching? The y is approaching positive infinity also on this end. All right, so that's a lot of properties to know. There are lots of things to know. And this was a quick refresh of completing the square and how you find zeros for quadratics. All right, next one is a rational function. A rational function, let's do that one. We have f of x equals x plus 3 over x minus 4. Now this has a denominator, and the denominator can't be 0. So if I'm going to find the domain for this, if I'm going to search for the domain, I know that x minus 4 can't be 0 because it's in the denominator. And so we can say x can't be 4. And so I know that my domain has to be, if I were going to do my domain, negative infinity to 4 in union with 4 to infinity. Now let's graph this, okay? Back in Algebra 2, when you graphed rational functions, well, you did a couple of things. First things first is you found the vertical asymptotes. Well, the vertical asymptotes occur when your denominator is equal to 0, and you can't cross it out by a removable discontinuity. So 1, 2, 3, 4, here's my vertical asymptote at x equals 4. And then how do I find horizontal asymptotes? Well, you put in a large number for x. If I put 1,000,000 in for x, I get 1,000,003, and I get 1,000,000 minus 4. If I put in 1,000,000,000 for x, these two numbers start not mattering much. And so you're going to get x over x, which is 1. And you do the ratio of their coefficients, because the degree of the numerator is 1, the degree of the denominator is 1. And so there we go. My horizontal asymptote here is going to be at y equals 1. Don't worry, next semester we'll go over those rules. And then I set the numerator equal to 0 because that's my 0. So when the numerator is 0, it's at negative 3. X equals negative 3. So here's my 0. And then I plug in x equals 0. That's a nice number to plug in. And I get, when I plug x equals 0, and I get negative 3/4. So it's right about here. And then with my knowledge of rational functions, I know that this left side has to look like this. And the right side, if I were to plug in a point, let's plug in 5. 5 plus 3 is 8. 5 minus 4 is 1. So 8 over 1 is going to be way up here. So it's going to look like this on this side. Whoops, I changed mid-graph here. There you go. Okay, so knowing that that's what our graph looks like for the rational graph, we can skip to domain is negative infinity to 4, union with 4 to infinity, because we just figured that out. Now let's do the range. The range, all the possible y values go from negative infinity to what do we have to hop over horizontally? 1. So the range is negative infinity to 1 in union with 1 to infinity. All right, this function is not continuous. It's got an infinite discontinuity. At x equals 4. It's got no extrema, does it? Because I don't have any maxes or mins, and this function is always decreasing if you put your hand on the function. So the function is decreasing from negative infinity to 4 in union to 4 to infinity, and it has no extrema. And now extrema just means maxes and mins over the intervals there. So let's do our end behavior limits here. The limit as x goes to infinity of f of x, and the limit as x goes to negative infinity of f of x here. All right, so what happens as x gets really large? As x goes to infinity, my y is headed to, that's right, 1. And this one, as x goes to negative infinity, my y is headed towards 1. So that's a quick review of rational graphs. And I'll put a representation of it right here. 1, 2, 3, 4. 1. And here we go. We got our graph here and here. So that gives us a domain and range. All right. So speaking of domain and range, let's figure out what we have to do and when do we get in trouble with domain. Well, we get in trouble with domain when we have the 0 in the denominator of a fraction, when we have a radicand, a radical, I should say, a radical of even degree root, and it has a negative under the radical, and when the radicand of an even degree root is negative and in the denominator. And so these are the conditions. So if I have, and I just put 1 in this denominator, it could be anything. It could be 2, it could be 5, it could be x, it could be anything up here in the denominator, but I just made it simple. But to find the domain, I have to set whatever it is in the denominator, and I make it a white puffy cloud because those aren't scary. I have to set whatever the denominator is not equal to 0. And where it isn't equal to 0, I exclude it from my domain. Just like we did with the rational graph here, right? We excluded 4 from our domain. Well, what happens if I have an even root? Well, when you have an even root, you can't take the square root of negative numbers. So whatever's underneath the even root, the white puffy cloud, that isn't scary. You take that and you set it greater than or equal to 0 and solve that inequality. And that's what your domain will be. All right, number 3. What if you have the even root in the denominator? Well, you can't have a 0 in the denominator, so the only thing it does, it takes away the equality piece, okay? And then number 4 is reserved for logs. Now it says later, but we're going to talk about it right now. You can't take the natural log or the regular log base b of a number that is less than 0, less than or equal to 0. So when you want to find the domain, you're going to set the white puffy cloud or the log argument to greater than 0 in both of these cases. Okay, and now here's my disclaimer. You know, when the lawyers get on TV and they like to say at the end of a commercial, their fast talk of all the exceptions and everything. Well, here it goes. This is my disclaimer. Unless there's a combination of 1, 2, and 3 in one problem, if that occurs, you figure out what the possibility for domains are for each and choose the domain that parts that work for both all conditions. Well, I kind of botched it, but you get the point. Sometimes you can have combinations of these things in one problem, and I have a couple of challenging problems in the notes that we can work through. Okay, but these are the basic domain gotchas or dangers that you have to worry about when looking for what your possible values of x are for your domain. So let's do some practice. Okay, so here we go. We're going to find domain. Now, algebraically means we're going to figure out how to find the domain. All right, well, so I have 1 over x. Well, 1 over x, well, that's got a denominator. So I'm going to set the denominator x not equal to 0. Now, I like to do number lines when I do domain. And so x can't be 0, so I'm going to put 0 here, and it can't be 0, so I'm going to leave it open. But can x be anything else? Could it be 5, 6, 7, 8, negative 50, pi? Sure. So it can be any other number. All right, so I can say then that the domain is negative infinity to 0, not inclusive, union 0 to infinity. My experience is if you do a number line, 99.9% of students can read the number line and go to instantly to interval notation. So the number line is helpful for that reason alone. All right, well, what do we have here? In part B, we have 1 over x squared minus 9. Well, that's a denominator, and the denominator can't be 0. So what do? We say x squared minus 9 can't be 0. Now I like to factor x plus 3, x minus 3. This is the difference of squares, can't be 0. So that means x can't be negative 3 or 3. Well, then let's do our little number line here, -3 hasn't opened, and 3 hasn't opened, but could x be 10, 20, 1? Any of those numbers except for 3 and -3? And the answer is yes. So that my domain is going to be on the number line all the other values. So if I were to read it off the number line, the domain is going to be -infinity to -3 in union with -3 to 3 in union with 3 to infinity. Now my experience is if you don't do a number line, the majority of the mistakes come from people missing this middle interval. So be careful. That's why a number line is powerfully important. Okay, C. Well, that looks like that has a denominator which can't be 0. So here we go. We're going to say x cubed minus x squared plus x minus 1 can't be 0. And we can factor this one by grouping because I see a pattern. So I'm going to factor out an x squared out of the first two, and I get x minus 1 plus, there's x minus 1, not equal to 0. Then I'm going to factor the x minus 1 out of both terms, and I'm left with x squared plus 1. Can't be 0. Now I know I'm going to stop here because x squared plus 1, if I were to say x squared plus 1 equals 0, x squared equals -1. What do I notice right away? X squared equals -1. These are imaginary answers. And we're not ready to go there until next semester. So this has imaginary zeros. So this is what I call prime. And think about it. If you have the curve x squared plus 1, that's a parabola that opens up. Is it ever equal to 0? Well, no, it isn't. All right, so we're going to do a number line. What goes on it? Just the number 1. And then it can be any other number. So my domain here is -infinity to 1 in union with 1 to infinity. All right, let's change it up a bit. The next one, D, is the square root of x. Well, square root is an even root. So with an even root, I know that x has to be greater than or equal to 0. Now I do sign charts when I do inequalities and I solve inequalities. So this is how I do a sign chart. I figure out when this is equal to 0. Well, it's equal to 0 when x is 0. So I'm going to put a 0 on the sign chart, and it's 0 here. Now please notice I didn't put an open dot here because the 0 may be in the domain. We don't know yet. And then I superimpose what this graph is. This graph in real life is y equals x. This is y equals x. What does that look like? Well, y equals x looks like a line with a positive slope. There it is, y equals x. And the y values on that graph are negative over here, and they're positive over here. If I let x equal 5, it's positive, so that works. X equals -5, it's negative. So I can only take the even root of positive numbers or 0. So I know domain's going to be bracket 0 to infinity because I can only take the square root of the positive numbers and 0. All right, let's try this one. F of x equals 7 minus x. And 7 minus x, since it's under an even root, has to be greater than or equal to 0. All right, so I'm going to do a sign chart. So what do you put on a sign chart? Well, you put the zeros of your function. What are my zeros here? Well, the 0 of this is 7. So I'll put a 0 there. Now, if I'm going to superimpose this graph on there, let's think about it. 7 minus x. In your mind, that has this negative slope. It's a line with a negative slope. So here it is. I'm superimposing my line with a negative slope. All right. What kind of y values does it have? Well, it has positive y values when x is less than 7, and it has negative y values when x is bigger than 7, like 9. If x is 9, then we have a -2 under the square root and can't do that. So the domain here is I can only take the square roots of the parts of the line that are positive. So it's going to be -infinity to 7 with a bracket. because I can take the derivative of 0. All right, we're going to amp up the difficulty now. So I've got an even root of the square root of 4 minus x squared. Well, what is 4 minus x squared? I heard it from the back. That's right. It's 4 minus x squared. It's a parabola that opens down. All right, well, that's 4 minus x squared has to be greater than or equal to 0 because it's an even root. I can only take the square roots of the positive pieces of that parabola. So let's do a sine chart because I'm doing an inequality. And what are the zeros here? Well, I've got 2 plus x times 2 minus x is greater than or equal to 0. And my zeros are 2 and negative 2. So I'm going to put them on my sine chart. Negative 2 and 2. And those are both zeros. And now I'm going to superimpose the graph of this parabola on my sine chart here. There it is. Now, can you picture that this being the xy plane, and you're not graphing the whole thing, you just want to know what the y values are. There's signs of them. Well, the y values are negative on this side, positive in the middle, and negative here. And I can only take the square root of the positive parts of that parabola, which are in the middle here. So the domain is going to be negative 2 to 2. I say positive, but it's positive and 0. All right. So now let's see what happens when we try to find the domain when I have an even root in the denominator. Well, the denominator can't be 0, but it's a square root, so it's going to be x has to be greater than 0. So I take the equality away because it's now a square root, but it's in the denominator. So let's do a sine chart. Here we go. So I'm going to put x equals 0 on my sine chart because that's when that's equal to 0. And this is the equation of a line, y equals x, which has a positive slope. So I'm going to superimpose that graph on here, on my sine chart. And then the y values on this graph, y equals x, are negative here, and then they're positive over here. And I can only take the square root of what kind of numbers in the real number universe? Just these, right? But it's exclusive because I can't include 0 in the denominator. So the domain on this one is 0 to infinity. Okay. All right. Looks like I have another parabola in the denominator. So this is going to be an even root. So it has to be x squared minus 3x plus 1 has to be greater only than 0, not equals, because I can't have a 0 in the denominator. Now, sadly for us, this doesn't factor. So what do we use? Well, we go back to the old tried and true quadratic formula. So let's see. X is going to equal the opposite of b, which is 3, plus or minus the square root of b squared, which is 9, minus 4 times a, which is 1, times c, which is 1, all over 2a. So that's going to be all over 2. So this is x equals 3 halves, plus or minus the square root of, this is 9 minus 4. So it's root 5 over 2. So those are my two zeros. So we're going to do our sine chart. Because I can only take the square root of the positive pieces of that parabola. So what goes on my sine chart? Well, my zeros. So it's going to be 3 halves minus root 5 over 2. That's a 0. And 3 halves plus root 5 over 2. Now I knew the one that went on the right was the positive one, and the one on the left is the negative one. And that's also a 0. And then what shape is this? Well, this parabola is x squared minus 3x plus 1. Opens up. So I'm going to superimpose that one. It's an open upright parabola. And what's my sine chart going to be? Well, my sine chart has positive y values on the left. In the middle, negative, and then positive y values on the right. So we can take the square root of the pieces of this parabola that are positive. So the domain here is going to be negative infinity 3 over 2 minus root 5 over 2. And this is exclusive because I can't be 0 in the denominator. Union 3 halves plus root 5 over 2 to infinity. So that's our domain for that one. And now, this is absolute value of x squared minus x. So we got to go back in time and remember, is that one of our restrictions? Do you see absolute value anywhere here? No, I don't even see a denominator in this one. So guess what, folks? This domain is all real numbers because it doesn't have one of the restrictions that we have to worry about. All right. What about J? This is f of x equals the cube root of 7x squared minus 5x. Well, the cube root is an odd root, which is not on our list for domain gotchas or domain dangers. So this one, too, is also all real numbers, its domain. Now, this one is a cube root, but where is it located? You're right, it's the denominator. So we can say that the cube root of 2x minus x squared can't be 0 because it's in the denominator. But it's a cube root, so it doesn't have to worry about having negative numbers under there. So we're going to cube both sides, and we get 2x minus x squared can't be 0. I'm going to factor, pull out a GCF, which is my x, and I'm left with 2 minus x can't be 0. So x can't be 0 or 2. So let's do our number line. Now, I don't do a sign chart on inequalities where this is not equals, or, when it's not equals. I do a number line. So this is 0, can't be 0, and it can't be 2. But in the denominator, it can be any other number. So the domain here is negative infinity to 0 in union with 0 to 2, in union with 2 to infinity. Now, you notice this is not equals. That requires a number line. Inequalities like greater than or less, greater than or equal to, those all require a sign chart. Why? Because you can't take the square root of negative numbers. So you got to know when the curves are negative. So you can exclude those from your domain. All right, let's do some more challenging ones. Wow. Well, this one looks like I have an even root in the numerator, and I have a denominator. So I have two of those conditions. So let's take the easy one first. X minus 6 can't be 0. And, because both conditions must hold, an even root in the numerator, so this is x minus 4, has to be greater than or equal to 0. So x can't be 6. And then let's do my sign chart here. So in this case, I'm going to combine a sign chart with a number line. So I know that x can't be 6. I'm going to put an open dot here. And this says, well, what are the zeros of x minus 4? Well, the 0 here is 4. So we're going to put a 4 on here and put a 0. And if I superimpose that graph, x minus 4, think about it, x minus 4, y equals x minus 4, that's a line with a positive slope. And if I were to do a sign chart, well, the negative parts of this line are going to be over here. And then the positive parts of that line are here. And I'm going to hop over 6 because I can't include 6 from the denominator's contribution to this domain. So now I'm going to read the domain right off of the sign chart number line. So I can take the square root of the positive numbers here that aren't equal to 6. So my domain, and it can equal 0 too. So it's going to be from 0 to 4. I'm sorry, try again. Right? It's going to be from 4 to 6, exclusive, in union with 6 to infinity. And I've taken care of the denominator and the even root in the numerator. All right. So what's interesting about letter B here? Well, I have a denominator only. So I have to say that x square root of 36 minus x squared can't be 0. And I'm taking the even root of this underneath here. So 36 minus x squared has to be greater than 0, and it can't be equal to 0 because it's in the denominator. So I would say this, x times the square root of 6 minus x times 6 plus x Can't be 0. So when is it equal to 0? Well, 0, -6, and 6. So on my number line, combined with my sine chart here, I'm going to put 0, I have a 0. -6, I have a 0. And 6, I have a 0. But I can't be those numbers, so I'm going to have those as open. Okay, now I choose to have those open because I have an not equals here. Now let's figure out what this parabola is doing. This is 6 minus x times 6 plus x is greater than 0. Now I can only take the square root of the positive pieces of that parabola. So let's superimpose the parabola. The parabola is going to be negative because it opens down. Does everybody agree that 36 minus x squared opens down? All right, so let's do our sine chart around the open dots here. When I do that, I have negative y values on the parabola, left of -6. In between -6 and 0, the y values are positive. And then I hop over 0, and they're positive again. And then they are negative, and I hop over 6. So I can only take the square root of, the positive numbers. So it's going to be, the domain is going to be -6, 0, union 0, 6, and that's exclusive. Now, let's try this next one. This next one is x cubed minus x squared, and it's under the square root, so it's an even root. So the x cubed minus x squared has to be greater than or equal to 0. And yes, we're going to factor, and we're going to get x squared. That's the GCF, and I'm left with x minus 1 greater than or equal to 0. So what are the zeros? Well, we have x equals 0 is a 0, and x equals 1, that's a 0. So we're going to put that on our sine chart. Here we go, here's my sine chart. And we're going to put 0, and we're going to put 1. Now we need to talk about the multiplicities of these zeros here. The multiplicity of this 0 is 2, and this one is 1. Now, back when you were learning about polynomials and graphing them, the multiplicity of 2, 4, 6, or 8, or something like that, that's an even numbers that bounce. And a multiplicity of 1 is a pass-through 0, meaning it's going to pass through the x-axis. Okay, so x cubed minus x squared is a cubic function that has n behavior like this, because it's a positive cubic. And so if I were to superimpose my graph, I would go from negative infinity, and at 0 I have a bounce because it has a multiplicity of 2. So we're going to superimpose the graph. There it is. It's bouncing at 0, and then it's going to come back down and then pass through at 1. And that's a cubic. And I'm going to do a sine chart. We'll have negative y values to the left of 0. I have positive y, negative y. That's a negative, and then positive to the right here. Sorry about that. And I can only take the square root of 0 or positive numbers. So the domain here is going to be, if I read it off the chart, we got to be careful because I have a 0 here standing all alone in the middle of these negative signs. So how do you write a single value? Well, you put brackets around it. There it is, 0. Union with brackets 1 to infinity, because I can take the square root of all of these numbers. All right. Of course, like I always tell you guys, trig never goes away. So in this case, I have an even root, and I've got the square root of sine x plus 2. So sine x plus 2 has to be greater than or equal to 0. Whoop, I don't know why I put it over there. So what I want to do is show you, we're going to go back in time, and we're going to graph y equals sine x plus 2. Well, that has a midline of 2. Here it is, midline of 2. And it's got a period of, the b factor here is 1. So the period is 2 pi, because it's 2 pi over b. I'm going to put a 0 here, and I'm going to put a 2 pi here. And then in the middle is pi, and then pi over 2, and then 3 pi over 2. And its amplitude here is 1, so it's going to go up 1 and down 1. So this is 1, 2, 3. And it's a sine curve, so the sine curves start on the midline. And since it's a positive sign, it's going to go up in amplitude to 3, back down to the midline, down in amplitude to 1, and back up to the midline of 2. So here we go. I'm graphing it. There it is. Now, what do you notice about this? Does this sine curve have any zeros at all? No, and all of its y values are above 0. So this thing right here is always greater than or equal to 0. So the domain here is negative infinity to infinity. Okay? All right. Well, what about this sine x plus 1? What's the only difference between sine x plus 1 and sine x plus 2? You're right, I heard it. Well, it has a midline of 1. So I'm going to do it on the same sketch up here, if that's all right, because they're so close. I'm going to do a midline of 1. Here's the midline of 1. And it starts on the midline. It has the same period because the period factor b is 1. And so we're going to start at 0, go to the midline, and we're going to go up in amplitude, back down in amplitude, and back to the midline. And if I were to graph it, you can't really see that this is green, but I'll make it red, so maybe we can see it better. So if we're going to graph that, there it is. And this goes back up, okay? So all the y values on this, so I would say sine x plus 1 has to be greater than or equal to 0. Well, this curve never goes below the x-axis. It hits the x-axis a couple of times. So this one's domain is all real numbers also, because it's always greater than or equal to 0, okay? Now this case is a little bit different. This is sine x has to be greater than or equal to 0. So let's do our own sine curve here again. So I'm going to go 0 to 2 pi, and this is pi over 2, this is 3 pi over 2, and then let's go negative pi over 2, and negative pi, okay? So the amplitude on this one is 1 and negative 1. All right, so let's graph this one. Pull my colors out here. We'll do red. Okay, so I get 0, up in amplitude, down, negative 1, back up to the midline. And then we're going to go down to negative 1, back up here. Okay, so here I am graphing my sine curve. But I'm taking the square root of all these y values, and I can only take the square root of the positive ones. Well, that's interesting. The positive ones occur between 0 and pi, and then from 2 pi to 3 pi, if I were going to do this again, right? So I would say the domain is, well, what's the first one? The first interval where I have positive y values is, and I can use a bracket here, is 0 plus, where do I start the next positive interval? I started at 2 pi. So this would be 2 pi n, an element of the integer set. And then where do I end the positive y values on this sine curve? I end them at pi, so that would be pi plus, and when do I hit the end of the next interval? At 3 pi, which is 2 pi away. So this would be 2 pi n, and an element of the integer set. Okay, so every time you increase n, so when n is 0, you get 0. When n is 0, you get pi. So that's the first interval here where it's positive. If I let n equal 1, I get 2 pi. That's the start of the next positive interval. If I let n equal 1, I get pi plus 2 pi, which is 3 pi. That's the end of the next positive interval. So that's what my interval would be. What happens, I'm going to extend just a little bit, if I had f of x equals 1 over the square root of sine x. What's the only difference here? The domain situation is going to be sine x is greater than 0, so the only thing different is it can't be 0. So I would just have my domain as the open interval instead. Right? Because it can't be 0, and that's what happens on the zeros. All right. A couple more topics here. Actually, I think that's all I'm going to do for this video. And then we'll continue to part 2, okay? So you guys have a great day. Thanks for listening.